This video covers several different tests of heteroskedasticity. So the null hypothesis in each of these cases is homoskedasticity, meaning that the variance of the unobservable error conditional on any combination of the explanatory variables is constant. So it's important to note that when you're testing for heteroskedasticity, you're assuming that you're maintaining the other first four Gauss-Markov assumptions: linearity in the parameters, no perfect collinearity, zero conditional mean, and random sampling. Particularly if the third assumption is violated, the zero conditional mean assumption. A test for heteroskedasticity can incorrectly reject the null, which is homoskedasticity, even if the variance of the unobservable error conditional on the explanatory variables is constant. And this can happen because of model misspecification. For example, if properly modeling the data meant a quadratic term, this was omitted from your model, or if you failed to appropriately log the dependent variable, for example. So the first step in testing for heteroskedasticity will be visualizing the data. And the data we're going to use today is Paige Fortna's Peacekeeping and Civil Wars dataset. In particular, we're going to look at the relationship between truces and conflict recurrence. So I can run some basic summary statistics to look at the distribution of these variables. We're going to run a binary response model. So both of these variables are binary. Our y variable is going to be binary. And so it's important to note that when the dependent variable is binary, the model must have heteroskedasticity unless all the slope parameters were zero. So it's very likely that we're going to find heteroskedasticity in our model. Truce has a positive and statistically significant effect on conflict recurrence in 1 calendar year. This constant tells us the probability of conflict recurrence where there's some other sort of conclusion to the Civil War besides a truce. And then the effect of truce is about 0.263 plus 0.092. So the coefficient on truce and the coefficient for the constant, or for the intercept. And added together, these are about 0.355. And that is the probability of conflict recurrence in 1 calendar year, given that there's a truce. So the first step is to calculate the residuals. And we are going to square these residuals. We're going to plot the residuals squared on the y-axis and our independent variable truce on the x-axis. Since these are both binary variables, you're going to see this spacing here. And even so, you can connect these dots and see a bit of a fan, which suggests that there is a problem with heteroskedasticity. Also, fit a line. So this suggests that there's probably an issue with heteroskedasticity in the model. So our first test is the Parks test. So most of these tests take the form of running your basic regression, then calculating your residuals, and then the third step is usually running an auxiliary regression with some form of the residuals as your dependent variable. So in Parks' test, you're going to use the natural log of the squared residuals as your y variable in your auxiliary regression. So once we calculate the natural log of the square residuals, we can run the regression of the square residuals on truth. And if the coefficient on truth is statistically significant at conventional levels, we reject the null hypothesis of homoskedasticity. So truth is significant at over a 99% confidence level, so you can reject the null hypothesis of homoskedasticity. Another test is the Glazier's test. In this case, we're going to calculate the absolute value of the residuals, and then in our auxiliary regression, we're going to regress the absolute value of the residuals on our independent variable. If we had more than one independent variable, we can include as many independent variables in this auxiliary regression as we thought were possible sources of heteroskedasticity. And again, if the coefficient on this variable is statistically significant, so if the coefficient on truth is statistically significant, we can reject the null hypothesis of homoskedasticity. So once again, the coefficient on truth is statistically significant at over a 99% confidence level. So we reject the null hypothesis of homoskedasticity. Another test is the Spearman's rank correlation test. So you use the Spearman command to rank the residuals, and you can do this either on the y variable or on your x variable that you believe is the source of heteroskedasticity, which is truth. So the p-value is less than 0.05, so we can say at conventional levels, in this case at over a 99% confidence level, we reject the null hypothesis of homoskedasticity. So a bit of a longer test is the Goldfield Quant test. And again, this begins running the regression from your main model. Then you sort the data according to the variable that you believe is the source of the heteroskedasticity. Next, you divide the data into several parts, typically 3. Then you run the regression from the bottom part of the data and the top part of the data, omitting the central part. And in each of these regressions, you're going to pull the residual sum of squares and calculate the ratio of the residual sum of squares from the bottom model and the top model to get our R. Next, you would compute your F statistic, and then you compare these. So if your R is less than your F, you fail to reject the null hypothesis of homoskedasticity. But if your R is greater than your F, you reject the null, which is homoskedasticity. So now I'll walk you through this. So we run our regression. We sort the data according to truth, which is our source of heteroskedasticity in the model potentially. Then we divide the data into 3 parts by creating an index. So this just numbers every observation in our data. Then we run our regression on just the bottom portion of the data. So when we divide our data into 3 parts, each part will have 64 observations. So we can pull just these bottom 64 by adding if index is less than 65 to our regression model. Then we use these next 2 lines of code to pull the residual sum of squares from the regression. And we run our regression for the top model. So for the cases 129 and above, and again, we pull the residual sum of squares from this model, and finally we compute their ratio. So the residual sum of squares from the first model is about 6.23. From the second model, it's about 14.19. And so the ratio of these, so the second RSS over the first RSS, is about 2.28. So next we calculate our F statistic, where our N is the total sample size, so from all parts of the data, which is 192 observations. And then C is the number of dropped observations, which is 64, and K is the number of regressors in the model. Which in our case is 2, including the constant. So if we calculate that, this gives us 64, 64, and then our 0.05 is just the confidence level that we would like to use for this F. So again, if our F is greater than our R, we would fail to reject the null of homoskedasticity, but our R value is greater than our F, and this indicates that we can reject the null hypothesis, that there's an issue with heteroskedasticity in our model. So another test is the white test. And so the white test is a specification robust test, which means that it doesn't assume a specific functional form for your heteroskedasticity. So if you're not sure what the form of heteroskedasticity truly is, which in most cases you probably don't, white is a robust test to this. So again, you start by running your model, and then you would calculate your residuals and square them. I've already done this. Then next, you're going to create new explanatory variables for your auxiliary model. And these are going to be squares of each of the x variables, as well as the cross product of the x variables. And so I've added pk done, which is a binary variable with a value of 1 if peacekeepers were present in the civil conflict, and 0 otherwise. So typically, you would calculate square of these terms plus their interaction. I'm going to do this to show you what you would do in most cases, but of course, since these are binary variables, their square is identical to their value when these variables are not squared. So you can see what happens in the model when we do this in a second. But so this is what you would typically do. So now we're going to regress our residuals squared on this new set of explanatory variables. And this model includes the constant. So now, of course, since the square of these variables is identical to the original form of the variable, the state is going to omit them because of perfect collinearity. So next what you would do is you get the sample size and the R squared. And we use this to construct our test statistic, which is the n times the R squared. So again, our n is 192. This is our R squared, and this is our n times our R squared. So next, we would look at the chi-squared test with k minus 1 degrees of freedom, with k being the number of coefficients in the auxiliary regression. So we have 6 coefficients including the constant, so a total of 5 independent variables. And we want 0.05, we're going to set that as our confidence level. So a 95% confidence level. This computes our chi-squared value. And then we compare this to our n times our R squared. So if our n times our R squared is less than our chi-squared, we fail to reject the null hypothesis of homoskedasticity. So looking back, we can see it's the reverse. Our n times our R squared is greater than our chi-squared statistic. So again, we reject the null hypothesis of homoskedasticity. So now that I've shown you the pattern of how to break out the residuals and regress them in our auxiliary model, I'm going to show you how to run the Borch-Pagan-Godfrey test, as well as the Bassett test, just using a simple command in Stata. You can also use this command to compute the White test as well, but now you've seen the actual form and how to do that. So you can follow this if you would like to actually construct each of these tests as well. So the Borch-Pagan test and the Corner-Bassett tests are implemented as tests on random coefficients. So both of these tests, as opposed to the White test, assumes a specific functional form for the heteroskedasticity. However, the difference between the Borch-Pagan and the Bassett test is that the Borch-Pagan is sensitive to normality, so it's assuming that the error term is normally distributed. And as we already know, that this may be a problem. And if it's non-normally distributed, but we assume that it is normally distributed, we may incorrectly reject the null hypothesis, even when the unobservable error conditional on the explanatory variables is actually constant. So first we'll see the result from the Borch-Pagan test. And again, it's less than 0.05, and this tells us so we can reject the null hypothesis of homoskedasticity. If we wanted to get all of the different tests in Stata, you can just use comma all after you run your IV head test. And so the way it's calculated here, these two are actually collapsed, And in both cases, we see that there's no difference. Again, this is because this is a binary response model. And so unless all the slope parameters were zero, which is fairly unlikely, you are going to have an issue with heteroskedasticity. So anytime you have a binary dependent variable, you should assume that there's going to be an issue with heteroskedasticity as a starting point, and so you should use that knowledge to then explicitly test and use these tests to create fixes for your heteroskedasticity.